Hello, my name is Gavin Courtright, and today I'm going to be presenting on 2D materials and their applications in gas sensors. So, a brief introduction for 2D materials. Graphene was first characterized in 2004 by these two guys at the University of Manchester, and that's the structure of graphene there on the right. It's a hexagonal lattice of carbon atoms in a two-dimensional. And it has unique properties over its bulk counterparts, including a very high carrier mobility, theoretically as high as 100,000 centimeters squared per volt per second. And obviously, since it's a 2D material, it has very high surface area. And layers of different 2D materials are typically stacked to form van der Waals heterostructures, which have unique properties from the individual layers of 2D materials. And research has diversified since 2004, but graphene has remained dominant. So graphene is very good at sensing things down into the parts per billion range, but it suffers from poor selectivity. So basically, it can sense almost anything, but it can't really distinguish between different molecules. So this can be solved by layering TMDs or TMOs on top. And you can see on the right here, we have two heterostructures, one with the TMO, which is manganese dioxide, and one with the TMD, which is molybdenum disulfide. And these types of sensors have very rapid response and recovery, which is usually on the order of seconds, which is much faster than the typical gas sensors that we have now. And these sensors function based off of the resistance of the heterostructure. And the change in resistance that occurs when a target gas or liquid or protein or anything comes into contact with the heterostructure. So for my project, I analyzed 5 different heterostructures. I analyzed them optically using an AM scope polarizing microscope. And you can see the picture in there on the bottom left. The camera is on top and the polarizer is on the back. Then I used an oscilloscope 4-point probe to measure the different resistances. So the first heterostructure I analyzed was an epitaxial graphene sample on M plus SiC. And then I did a molybdenum disulfide on epitaxial graphene. And on the left there, you can see the nanoflowers of the molybdenum disulfide. The TMDs typically deposit on the graphene in sort of a nanoflower type shape where you see those little dots. And then on the right, that's the epitaxial graphene that you see. And then this image was provided by Dr. Daniels. This is quasi-freestanding epitaxial graphene. So it's slightly different from the epitaxial graphene. A little bit more variance there. This is more zoomed in too. And then this is a manganese dioxide. And it doesn't really have the dot deposit pattern that the TMDs have. It kind of looks like shattered glass a little bit. And then this is a manganese diselenide deposited on the manganese dioxide. And those little dots that you see are the manganese diselenide. And they're easier to see on the left, but there's one little one on the right there in the bottom. So these are my results for the sheet resistance, which is the more important part of the research. And so as you can see for the M plus SiC, the electrical properties were divided into 2 regimes, where at a low current, we had a higher resistance, and then at a higher current, we had a much lower resistance. And this was caused by the M plus SiC, because at a higher current values, the electrical current would run through the M plus SiC, which has a much lower resistance than the graphene heterostructure. And this was caused by the dangling pi bonds. So here we have, on the top, we have epitaxial graphene, and then on the bottom, we have quasi-freestanding graphene. And so the substrate and the graphene are kind of connected. So epitaxial graphene goes with M plus SiC, and then quasi-freestanding graphene goes with semi-insulating SiC. So when epitaxial graphene is first synthesized, it has these pi bonds and these dangling bonds connecting it, as you can see, to the substrate, to the SiC. So that buffer layer of epitaxial graphene is connected to the SiC, which allows current to flow through, which is what we saw here at the high current regime. The current was flowing through these bonds. But then when you flood the system with hydrogen at very high temperatures, usually around 1,000 degrees Celsius, the pi bonds kind of get cleaved, and then the dangling bonds get capped by the hydrogen atoms, as you can see here. And this does not allow electricity to flow between the two. And so as you can see here, we only have one set of resistance values for the quasi-freestanding epitaxial graphene. And there's some other electrical properties. Quasi-freestanding epitaxial graphene is very favorable. It has a variety of electrical properties which make it a little bit better than epitaxial graphene. But and one of those is not having the dual regime behavior. But there's a bunch of others as well. So the use of M plus SiC as the substrate will add complexity to the sensor design because you have two different regimes that you kind of have to account for, which makes it more complex than with the semi-insulating SiC, where you only really have one that you have to worry about. And the choice of substrate could affect sensor response time. So when you have the lower resistance values from the M plus SiC in that high current regime, where it's orders of magnitude lower than you would typically see for a graphene heterostructure, that could make your sensor response faster just because the electrical current can move quicker through the medium. And then semi-insulating SiC may be preferred because it doesn't have the complexity from the dual regime. And in fact, it is preferred, and it is generally what scientists in labs, including the Daniels lab, are moving towards. And further experiments could be conducted to examine other electrical properties, including, well, specifically the Hall mobility, and see if there's a difference in the Hall mobility between the two substrates. And I would like to acknowledge Dr. Daniels and his lab group for providing me with the samples, and also Trend for providing me with the equipment. Thank you all for listening.